So let's do a few calculations using our first order kinetics. So let's start with this problem here where we want to date a rock sample. This rock sample contains both uranium-238 and some lead-206. Remember that the lead-206, at least in this example, was produced during the decay of uranium-238. So we could say that this lead used to be uranium. And so we have this rock sample that contains 1.3 times 10 to the negative 5 grams of uranium-238 and 3.4 times 10 to the negative 6 grams of lead. So the question is, how old is the rock? And so we're going to use our equation to find out the age of the rock. And we know the half-life for uranium-238. 4.5 times 10 to the 9 years. And anytime you have the half-life for first order kinetics, it's very easy to convert the half-life into the rate constant. So we're going to find T. We have our rate constant. We know how much we have now. We know how much uranium we have now. What we don't know is how much uranium we had to start. When was the rock formed? How much uranium did we have when that rock formed? So what we need to do in order to find the amount of uranium-238 in the original rock when it was formed is we need to convert the lead-206 back into uranium. And we do that with this calculation here showing that if you had 206 grams of lead-206, that translates into, if you considered the decay, to 238 grams of uranium-238. So in this calculation, we convert that lead back into uranium-238. So what we had initially when the rock was formed was the uranium we have now plus uranium that decayed. And so N naught is 1.7 times 10 to the negative 5. So I calculate my K using my relationship between the half-life and the rate constant. And I get the K there. I put it into my formula, and I find that the rock is 1.8 times 10 to the 5 years old. So let's do another calculation here. What if we had a piece of charred wood that was buried in some sediments? It's possible I could use this charred wood to date the sediments. And this piece of wood has a activity of 5.22 disintegrations per minute per gram. So this is a unit that we can use to define how radioactive something is. If we were to take a living organism today, what we would find is that activity would be 15.3 disintegrations per minute per gram. And so what we're going to do here in this calculation is use what living organisms have in terms of activity and relate it to the decayed material in the charred wood. And so we know the half-life of carbon-14, And we can easily convert that into a rate constant that we can put into our equation. So we're going to calculate the time in terms of how old this charred wood is. And so we need to figure out what to put in for N naught and what to put in N. And this might be a little counterintuitive, but N naught is today's activity, because we are again assuming that the charred wood in our simplified calculation had a activity of 15.3 when it was alive. And so that ends up being our N naught. And then our time now, or the amount that we have now, is 5.22. So this ratio of N over N naught should always be a fraction. It should never be greater than 1. So we do the calculation, solve for time. I get 8,900 years. Let's do one more with carbon-14. So let's say we found some animal scat in a cave somewhere. And we want to kind of know how long ago was that animal using that cave. And the other piece of information we're given is that the carbon-14 to carbon-12 ratio is a fraction of what we would find today. It's a fraction of 0.714 of what we would think would be in the atmosphere today. So how old is the scat? Well, let's use our equation again. Solve for time. We can find our rate constant from our half-life that is known. And so we just need to figure out what the ratio is. And given this information, we could say, well, when the animal left its scat, we would give that a value of 1. That would be what we're assuming here, is that similar to the amount of carbon-14 that we have today. And then over time it decays, and it's decayed about 30%. We're at 0.714. So we set this up. Again, this is just giving you a different view of what type of information you can put into N and N naught to calculate the age of something. And so we get 2,700 years, or 22,780 years. So last example, let's date some marine sediments. So this one is a little bit trickier. We are going to use thorium-230 to date some marine sediments. This is a very common way to date marine sediments. And we're going to make some assumptions. So first of all, there's quite a bit of uranium in seawater. And so most of it is uranium-238, and it's in this form here. And this is the ion that floats dissolved in the ocean, the uranium species, and it stays in the water column for a very long time. It has a residence time of 500,000 years. So what the distribution of uranium-238 looks like is this. It's just a straight line. It's a straight line with respect to depth. So it's what we call a conservative element. However, we know that uranium decays into thorium-234 and then thorium-230. But once it turns into thorium-230, it immediately turns into this species here, which is a thorium hydroxide species. Now, this species is very particle reactive. It instantly absorbs onto particles that are raining down from the surface, and it sticks to them, and these particles sink to the bottom of the ocean, and they do so very quickly, on the order of 300 years. So if you compare these two residence times, you would say that the residence time for thorium is very quick and also very short with respect to the half-life. So this 300 years is pretty much, on a geological scale, instantaneous. So what we can do is use this chemistry of thorium, where here we see, again, dissolved thorium-230 instantly falls out. The dissolved falls out of solution, and it's into the marine sediments. So we could say that the layers of marine sediment can be dated with thorium, because as they deposit, that is also when the thorium-230 starts the clock. It gets formed from the decay of uranium-238, and then it itself has a half-life, which we can use as a dating tool. And so here's our example. So we have thorium-230 activity, and it's measured in marine sediment. The top layer of the core has an activity of 62 disintegrations per minute. And at a depth of 1 meter, the activity is 28. And that makes sense. The depth, the sediment layer at 1 meter is older than the surface, therefore it has a lower activity. And so from this, let's determine the age of the sediment and the sedimentation rate. So we're given the half-life. So this is what we should expect with respect to depth and activity. We would expect a higher activity at the surface, and it would exponentially decrease with depth. Or if we took the natural log of the activity, it would be a straight line when plotted with depth. So there are other issues that we would consider if we were doing this in a real research environment. We would take into account, other isotopes that could help us do corrections. So the actual measurement that research labs do is much more complicated, but we're going to ignore those complications. And so just like our other problems that we've done, we're going to use our equation here. We're going to calculate K from the half-life, and we're going to find out how old that sediment is at a meter's depth. And we find that it's 86,200 years. So what's the sedimentation rate? Well, I will say that most of the time sedimentation rates are measured in centimeters per 1,000 years. And so the sedimentation rate is going to be the sediment thickness divided by the time. And so we have a thickness of sediments of 100 centimeters. And we know that it took 86,200 years. So I'm going to put it in this form here of 86.2 thousand years. And so the sedimentation rate is 1.16 centimeters per 1,000 years.